Sorry about that, Infinity P. I was paying attention to what I was doing instead of what I need to be doing. Today is the 17th. Got okay. Now I've got two people up there. Do you have any questions before we get started? We got a whole 5 minutes before class starts, of course, but uh I signed in early just in case anybody had questions. Plus, I'm forever coming in late, so at least I can do is show up early every now and again to make up for it. I sent that chat only to you, Infinity P. All right, Kim and Caroline, I've already asked Infinity as well, but if y'all have any questions, feel free to ask me. We still got about 2 more minutes for class starts, and there's literally only 3 people in here other than myself.
I actually did have a quick question.
Yeah.
Um, so in lab the other day, our lab professor was talking about us taking our lecture tests in lab. But I guess I had assumed we were going to take them with the online proctor, through the lockdown browser. I just wasn't sure because she said it might have changed from last semester because it was Mondays, not Thursdays, and yeah.
Gotcha. Yeah, so this time we've scheduled 3 face-to-face exams. Actually, I'm gonna double check. 1, 2, 3 plus the final we've scheduled at lab times. So there will be three face-to-face, up to three face-to-face, quote unquote, midterms, plus a final exam, all of which will be done at our lab location on our lab day. And your lab instructor, since you don't have me, your lab instructor will administer my test. What I usually do is I usually make them a Canvas test, and you still have a Respondus lockdown browser you got to use. But other than that, you do it in the classroom uh, with that teacher mining you because believe it or not, even with that setup, we still have people cheating. So so we just keep up with it that way.
Okay, so we're still going to be using the Respondus.
Hmm. Yes, we will
Okay.
still use the Respondus even for the in-class face-to-face test, unless I happen to do one on paper, but I haven't done any on paper in a long time.
Okay, I was just curious because my the computer I have Respondus on has to be plugged in at all times because
Gotcha.
my it's very old.
Gotcha. Well, the good news
Yes.
is you can use that one, and there are plugs there in the lab. The other good news is that we also have the labs all set up so students can take those if their computer stops working, or a lot of times they'll get there and forgot their password and can't log in. So there's a bunch of different ways we could do that. But yeah, you will have access to that computer as well as your own.
And we can bring in our phones to take because it has like the two-factor authentication.
Hmm.
So
Oh,
we have
yes.
to
Yeah, you can bring
we
those,
can
but then you
still
got to
use
put them
that.
away. But yes, the
Yeah,
two-factor authentication, definitely you'll need that for it.
awesome. Just making sure. Thanks.
No problem. You're welcome, Caroline. Anybody else have any questions? We got more people here. We're up to like 10 people total. Whoop, 11 people total. I see Ronnie, Johnny, Mickey, and Mike. No, that's something else. Hannah, Julio, Jonathan. It's a bunch of unique names and unique ways of spelling them. I like it. Get crazy. Let's try some stuff. I want to name myself ZZXY2. That's gonna be my name. Also, I just look like that to me. Not
I
really.
had a quick question about the extra credit too.
Yes, go for it, Keaton. Is it Caden?
Yeah, it's Caden.
Gotcha.
So when it says like a hashtag over 3 feet per second or cubic feet per second, like hashtag
Hmm.
over gallon, like what does that mean?
The
Hashtag?
hashtag is another symbol that they use in engineering practice for pound. So if you ever see that, just read it as pound.
Okay. All
So
right, thank
that's,
you.
yeah, that's all that means. I did take in week two, I took away extra credit two, but extra credit two, I think, was identical in week one. So don't worry about it. If you'd seen extra credit two in week two, it was just the same thing as the extra credit I'd done in week two. So you didn't miss any opportunities or anything. So it's now 5:22, and one last time, anybody have any questions? All right. Well, I do want to get you guys on a schedule where you're sort of used to having your homework turned in every Sunday. So I just want to remind you that is the normal scenario because of various things, it being the first week of school and some other stuff. I did make this particular first two sets of a homework due at random dates. The extra credits are going to be due whenever. And what I do is I normally make them due like a week after I assign them. You can always turn them in by Sunday. And in fact, sometimes I don't even care about them being late. The main thing is if you do an extra credit and you do it before I grade it, then I'm probably going to count it without taking any points off or anything like that. Because you either with a extra credit, you get 100 or nothing. So in general, I often count them if I haven't graded it by the time you turn it in. The other thing is with the extra credit, the reason I normally assign those extra credits is because it's doing something that helps you in the real chapter that we're on. Ugh. On the chapter that we're on at that time. So if you do them much more than a day or two later, you're sort of shooting yourself in the foot in terms of getting the experience that the extra credit gave you. So I would definitely prefer and suggest you do it like as the same day that I assign it, but definitely by the due date on there. If you don't, I'll probably still give you credit and you'll still get extra credit and all that good stuff. It's just like I said, a lot of times I do that to help you better understand something about the chapter. Other times I just do it for fun. Like one of the problems I gave was divide 1 by 243, which is division problem that I learned from Richard Feynman that happens to be kind of neat, and hopefully you'll like it. So other than that, the rest of the semester, just always plan on there being at least 2 assignments due every Sunday at 11:59 p.m. and that'll keep you from running into problems. At that same time, you might also want to check the extra credits and knock those out as well, because they're not always necessarily due at 11:59. And I would normally make that, but that sometimes puts a little too much on you where you feel kind of a little bit too much pressure. So that's why I just usually put them a week after I assign them. But other than that, just try to get everything done by 11:59 on Sunday, and the semester will go much more smoothly. Now, we did chapter 1 last time. I've done quite a few examples. You can also see examples on my YouTube channel. If you look in there, for instance, there's not that one. I'm looking at them. Not that one, that one. There's one called Converting Units, Unit Analysis, and Dimensional Analysis. That's the one I would recommend you guys doing if you want some extra experience with the stuff from chapter 1. Of course, chapter 1's already been turned in and that sort of thing, but I just want to let you know that that is an option for you guys to check it out. Plus, there's other videos in there, but that one was done just, like I said, a few days ago and should help you. So we're going to go ahead and start into chapter 2. And chapter 2 is called Describing Motion, Kinematics in One Dimension. And I'll tell you that kinematics is a branch of what we call mechanics. Mechanics is basically the science of physics where you're where you're trying to figure out what forces cause what kind of motion, and that entails things like conservation of momentum. It entails stuff like statics, dynamics, kinematics, all that good stuff. And in general, the mechanics itself is made up of 2 parts: dynamics and kinematics. The kinematics is what we're doing now, which is really just the study of motion without considering what actually has to happen for that motion to occur. Like I could give you an equation for the acceleration as a function of time, and it might be something crazy like 3t 3t squared plus 42t minus 27 or something like that. You can analyze that and tell me, if I give you certain initial conditions, you can tell me what the velocity is as a function of time. You can tell me what the velocity is at one particular point in time. You can tell me what the average velocity is over various times. You can also, again, if I give you the appropriate initial information, you can tell me what the position is as a function of time, what the change in position, which is something we're going to call the displacement, as a function of time. All those different things we can do, but without any knowledge of how that acceleration came to be. All that's the kinematics. The dynamics is when you employ F equals ma, or the other version of Newton's second law, which is F equals dp dt. So just to let you know, that's what we're talking about. And I'm going to cover up my camera so I can keep on yawning, evidently. So the chapters always start off with a chapter opening question. This one's sort of helpful. It says 2 small heavy balls have the same diameter, but one weighs twice as much as the other. The balls are dropped from a 2nd-story balcony at the exact same time. The time to reach the ground would be A, twice as long for the lighter ball as for the heavier one. B, longer for the lighter ball, but not twice as long. C, twice as long for the heavier ball as for the lighter one. D, longer for the heavier ball, but not twice as long. Or E, nearly the same for both balls. We will learn that. This one isn't quite as interesting as what I found for some of the other chapters, but that one's pretty good. I suspect most of you know the answer to that, but you always want to ponder a answer for it, at least actively take the role to think about it, come up with it in your head. If you have a pencil that you can use to erase later, you might even want to write it in the margins next to it. And then when you reach the part of the chapter where you learn how to answer that question, you find out what the real answer is, and you either correct your logic or pat yourself on the back. That helps you learn. And that's the same thing when you're solving physics problems, is you want to try to take a poke at a physics problem, even as much as giving the answer, even if it's just a ballpark figure. Include the answer, make sure if it's a vector quantity that it's pointing in the right direction, you know, its magnitude, or if it's positive or negative, make sure you can tell whether it's positive or negative and you know what the units are. All of that process helps you better learn the science, and basically the big concepts of the science. So definitely do that. What we're going to start with, though, is in the first section of chapter 1, we talk about reference frames and displacement. So there's a lot of physics that can be done technically without any kind of coordinate system. In fact, ultimately what Einstein did in the general theory of relativity in 1915 was he introduced basically the general theorem of relativity, which basically says the laws of physics are the same for all observers. And what you mean by that, to some extent, is that no matter what coordinate system you use, the laws of physics are going to be the same no matter what or no matter what coordinates you use. And with that in mind, you can actually work a lot of the big fundamental equations without ever deciding what the coordinate system is, not deciding where the origin is, not deciding which direction is positive X, which direction is positive Y, which direction is positive Z, or any of that kind of stuff. So that's important all by itself. But a lot of times when you actually go to apply the equations, uh, it doesn't help you, and it's really hard to do applying the equations without an actual coordinate system chosen and an origin. So a lot of these times you're just going to have to realize that, one, you can choose any coordinate system at all, and two, sometimes you do have to choose a coordinate system. Now, think about it this way. You guys are facing me, I'm facing you, at least according to the screen. So in principle, that direction right there, which is to my right, I would tend to call that the positive X direction. I'd tend to call up the positive Y direction. But for you guys, that's literally exactly the opposite for the X. When y'all see it pointing this way, that should mean sort of like, if Zoom doesn't reverse the screen, that should, yeah, that should point in the negative X direction for you. And that's okay. It's perfectly fine for my coordinate to suggest one direction is positive and your coordinate system to say that exact same direction is negative. That's okay. Long as you stay in your coordinate systems, you'll get the right answers. And long as I stay in my coordinate systems, I'll get the right answers as well. So that's something to keep in mind. And that also physically tells you that, yeah, the nature of physics shouldn't be dependent on, who's doing it, or else this side of the road in my neighborhood would all know the laws of physics, and on the other side of the road they'd all be screwed up because they're all got the x-axis pointing the wrong way. Okay, so hopefully that'll help you. We'll get into coordinates and moving coordinate systems and stuff like that in chapter 3. But right now, I just had to introduce you to that. And I'll tell you that in general, we do draw the x-axis, like I said, often to horizontal and to the right is positive, and up is the positive y-axis. If that's the case, then we would say the z-axis is pointing out of the screen. So that's x positive, y positive, Z positive. The coordinate system has to be a right-handed coordinate system. And what that means is this finger, this is my right hand, this index finger pointing straight ahead is the direction of the x-axis. This middle finger, which I've got bent to 90 degrees, points in the positive y direction. And if those two, once you make your hand match x and y, then you have no choice but to say the perpendicular direction that my thumb is pointing, which is straight up, has to be the z direction. If you ever do that with your right hand and it don't match, you've got what's called a left-handed coordinate system, and there's a lot of little mathematics that falls apart and is basically just going to give you wrong formulas. So make sure you always choose a right-handed coordinate system. I tell you, we're probably not going to run into maybe one or two cases this whole semester where that would be a problem, but next semester it's going to be a lot bigger. So you might as well just get used to it. Just always remember coordinate systems have to be right-handed, or some of the formulas that you use in everyday life, like cross product formulas, have to be changed. So just always choose a right-handed coordinate system. Or notice this, if you just choose two coordinates, in other words, you don't have a third dimension, doesn't matter at all. There's no such thing as a right-handed or left-handed coordinate system. It'll automatically work every time, as long as it's just X and Y, or Y and Z, or X and Z. All right. Any questions on that? All right, so what we need to do now, in addition to knowing about that coordinate system, is I need to share my iPad screen with you, and I got to introduce some of the key terms that we use in kinematics, and therefore ultimately in mechanics. All right, it came up. So, for instance, and a lot of this, I apologize. When I say there's a definite difference between displacement and distance, that might not make much sense to you guys, but once you get into chapter 3, when we introduce vectors, it's going to make more sense. Okay. So there is a difference. Distance is just the amount of miles, meters, inches, or whatever that you've traveled. So distance the number of meters, centimeters, miles, kilometers, ... that an object travels. Displacement, however, displacement's a little different. Displacement is a vector, which you can think of just as an arrow, a vector. Now, I just mean a geometric arrow like you're drawing, not necessarily an arrow that you shoot with a bow. But what I'm saying is you can think of displacement as a vector quantity or an arrow, and it points from the object's initial position to its final position. So that's what displacement is. You can also use something like position, which is also equal to location. And that can be thought of as a vector. Again, think of an arrow. That is a vector that points from your coordinate origin to, actually I shouldn't say your, from, let me change that to objects. Now that made it a lot harder to fit that word in. I'm going to go ahead and do this to keep it from becoming bad, or worse, I should say. So it points from Happens every time. From an object's. Oh, actually, no, I should have said you're there. I forgot I was talking about the actual coordinate there. So yeah, let me go ahead and put that back. I apologize. I was thinking of a later part in the sentence. So from your, so you're talking about your coordinate system, your origin, from your origin to the location of an object. So that's what I mean when I talk about an object's position. You can think of it as a little arrow that points from your coordinate origin to that particular object. And then you can think of displacement. So like this, where displacement remember I said it's a vector. It points from the object's position, initial position to the object's final position. That displacement is often called delta x. And in 3 dimensions, we would put an arrow over it, either that arrow symbol or that arrow symbol right there. And it would be defined as your final position would just be the plane x minus the initial position, which would just be the x with a subscript 0 for initial. That's what displacement is. I will say that this letter, uppercase, Greek, delta, is defined in physics to be final minus initial. So what I mean by that is no matter what variable I put after the delta, you take the final of that variable and subtract from it the initial of that variable. Okay. So in 2 dimensions or 3 dimensions, those little arrow symbols are needed. In 1 dimension, you don't really need it, but you can use it. Again, we'll learn more about vectors in chapter 3, but I'm trying to give you an idea because displacement makes a lot more sense if you talk about it in terms of vectors than if you just talk about it like your book is doing, in my opinion. So in fact, what we can do is we can say if someone moves to the right, and we drew our positive x direction to the right, then we'd say that object has a positive velocity, and velocity is another vector quantity. So the fact that I specified in 1 dimension that it was going in the positive direction, that's already handled the direction. So that's what I mean. I don't necessarily have to put the symbol up there, and I can just specify the direction by calling it positive or negative. If the object was moving to the left, I'd put a negative, that sort of thing. Now, with that in mind, let me give you a little idea so you can sort of tell the difference. So I'm going to draw a coordinate system here. And my coordinate system is not going to be that fancy. Okay. This is going to be my x-axis, and that's measured in, say, meters. And this is going to be my y-axis. That also is measured in meters. And let's say I'm going to make some marks here to represent the numbers. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So that's my marks there. I'm going to say this is 1, 2, 3, and 4 right there. Now, what you might imagine is, let's say, consider you standing at the curb in front of your house and you having chosen that point as your origin. Also, assume you have called the direction to the right. Oops. The positive x-axis. In other words, you're standing out in front of your house, and you're right up where your grass meets your road, say, and you're looking across the street. What you're going to say is, where I'm standing right now is the origin. I look down the road that way, which is to my right, and therefore your right as well. I'm going to call that the positive x direction, and I'm going to call that over there the negative x direction. That positive x direction might correspond to north, depending on where your house is and what road you're talking about and all that good stuff. But the main thing is that's your coordinate system. So, and it's also your initial position. So what I'm going to do here is I am going to put a green dot to represent your initial position. Oops. Got a little excited there and drew my eye twice. So that's my initial position, or your initial position. And then you're going to walk such that each of these one marks is 5 meters. So for instance, what I'm saying is this is 5, 10, 15, 20, 25 meters, 50 meters, 75 meters, 100 meters, like that. Okay. So you're going to walk to here, and I'm going to say that is the position at which you turned around. And then you walked back another 30 meters, like so. So what I'm going to do is I'm going to represent the way you walked, the direction you walked. I'm going to introduce it with a purple line. So what you did was you walked all the way to here, and then you turned around, as I said, and walked all the way to here. And at that point, I'm going to say that you ended up right here. Your final position, just plain X. Okay, so evidently you walked out to your road. You decided to create a coordinate system just for the exercise. That coordinate system involved basically right below your feet was the coordinate origin. The x-axis pointed to your right, straight down the road. The negative x-axis pointed to your left, straight down the road. So you turn to the right and walk 100 meters. You stop at the 100-meter mark, turn around and walk backward, back the other direction for another 30 meters and end up, of course, obviously at the 70-meter mark right there. So anybody want to tell me what distance you traveled?
130 meters.
Exactly. And you said 130 meters? And I say, yes, sirree. That's absolutely correct. Okay. Now, anybody want to take a poke at what your displacement is?
Would it be 70 meters?
That's exactly it. Who is that? Is that Infinity answering that?
Yes.
Good job. Thank you. So what I would say, just to give you the right symbols and everything, is I would say delta x is equal to x minus x0, and that's equal to, of course, 70 meters minus 0 meters equals 70 meters. And again, that's exactly right. So I think from that alone, you can sort of see the difference between displacement and distance. Does that make sense to everyone? Now, if you actually wanted to know what is your displacement vector, then you'd first draw a vector to your initial position, which is supposed to come from the coordinate origin to the initial position. So that literally means from the origin to the origin. So the vector would just be like a dot right there at the origin. So initial vector. Okay. The final position vector would be 70 meters long as shown. So I'm going to do that now. So what I'm going to do is I'm going to draw a vector. I'm going to move it up along the y-axis just so I have room, but I'm not saying that I'm doing anything any different than what I did before. But this would be your vector x. And since I'm actually using the word of vectors, I'd go ahead and put arrow over top of it like that. This position, this little dot right here is x0 with an arrow over it. Okay. And delta x, of course, is just x minus x0. If I put that back in vector notation, then that's delta x is equal to the final vector minus the initial vector. And since the initial vector is just the 0 vector, you just get x final. So that red vector up there is your final position and delta x. That make sense? Okay, so that's the difference between displacement, position, distance, and all that good stuff. So distance is just how far you traveled. Displacement is about how far you traveled, but it takes into account the directions as well as the initial positions and the final positions. So for instance, if you put your foot down on home plate, like you're getting ready to bat, but instead of stepping in the batter's box, which is what you're supposed to do, you just start right on the home plate, and then you run to first, run to second, run to third, and then run back to home and stop right there on that home plate again. Then your distance traveled is basically 4 times 90, whereas your displacement would be 0. Does that make sense? So whenever you make a trip that starts and ends on the same position, your displacement's always 0, but your distance is definitely bigger than 0. Does that make any sense? Does anybody have any questions about that? Now I want to go one step further and talk about speed. So I will ask you, what units are on your speedometer?
Miles an hour.
Yes. And thank you for using the typical way we say it. We say miles an hour, but I want you to realize that if we're really careful, we want to try to say, actually, I'll do it in a different color. We try to say miles per hour. So what we normally call miles an hour is actually, by the way, I'm one that does that too, so I'm not trying to pick on you there, Hannah. That's just that's just the way we do it when in rural areas. It's miles an hour, darn it. So miles an hour is actually miles per hour. And I'd like to ask you guys, what does, and actually I should do this in a different color. What is miles a measure of? So is it a measure of time? Is it a measure of mass? Is it a measure of torque? Is it? I
It's a
heard somebody
measure
say
of distance.
Distance?
yes, distance. And I'll also ask you, what is hours a measure of? I bet y'all know that one. It's a measure of mass, ain't it? Hours measures a unit of
Time.
time. Very good. So I'll put time right there as well. And from your vast experiences with high school pre-algebra, high school algebra 1, high school algebra 2, all that good stuff, what does per mean? So we're talking about a mathematical operation. Anybody know what per would mean in that context?
Like how many times or something like that?
Yeah, like how many
Or
times
divided
does
by.
something go into it? There you go, Hannah. That's right. And that's often the key when you're solving word problems. For instance, if you're taking and putting something in it and then putting that same thing in it again and putting that same thing in it again until basically keeping count of how many times you have to put it in till you've completely used up whatever that is there, then you're actually doing division. So yes, the answer is division. So you don't need a formula for speed. What we're going to do is we're going to say average speed. Let me start it that way. Now, your speedometer says miles per hour, and you know miles is a unit of distance, and you know hours is a unit of time. So miles per hour should make you think of distance divided by time. And if you really want to clean the language up so it's absolutely clear what you're saying, you'd say distance traveled divided by time taken. Does that make sense to everyone? So distance traveled divided by time taken. And you came up with that formula just by knowing your speedometer units, right? I don't want you to think of physics as this whole new thing where I'm introducing new quantities and stuff like that. What I want you to do is every time you're introduced to something, hopefully you might be able to find something in everyday life that's just like it. And therefore you're not learning anew, you're just adding on to it something you already are quite familiar with, adding on a little bit better special understanding. So that's what average speed is. That brings us to another quantity, which would be instantaneous speed. If you wanted the instantaneous speed, that's a little different. So if you take the total distance divided by time, if I ran, for instance, let's say I ran a mile, which is pretty funny to think about, but but if I ran a mile, you can imagine some parts of the mile I'd run a little fast, like when the neighbor dog got after me, or sometimes I'd run a little slow, like when I'm trying to be nosy and figure out why the police are at such and such a house or something like that, so on and so forth. But you'd be quite confident that I did not run exactly the same speed all the time. But really, if I just take the 1 mile and divide it by the time, I'm getting a average, and that suggests there's one number associated with my motion, and that's not very reasonable. But if I used my phone and let's say one thing you can do, for instance, there's probably other apps that do it too, but I know Snapchat, you can open your camera as you're driving or riding down the road or something like that, and it will actually read your velocity in real time like it's a speedometer. So if you imagine me holding my phone with Snapchat like that and I'm running a whole mile, the instant I look at that reading on my Snapchat app, that is what we call the instantaneous speed. And that's quite different. The instantaneous speed is going to be a certain number at one time, a different number at another time, and in fact might be a whole infinity of numbers over the distance of 1 mile. So that's something we need to compare to. So average speed should be compared and contrasted with instantaneous speed. Okay, so I want you to think about that and make sure you have some understanding of it, and then try to think about when would the average speed be the same as the instantaneous speed. So that's another consideration. We don't do more than that with the idea of speed. We just know speed, which starts with S, is a scalar quantity. Okay. Now, the other thing we want to learn about is velocity. Specifically, average velocity. which would be V bar. Now, technically, I should say that this right here, all of these things are what we call vector quantities. And notice they start with V's as well. So that's just something to help you remember which one's which. A V for vector, a V for velocity, a S for scalar, a S for scalar. And if you go back to Despicable Me, you'll know that the villain in Despicable Me, does anybody recall what that villain's name was?
Vector.
Vector, yeah. And he actually gave a correct definition. He said, it's a mathematical term. It means an object with both magnitude and direction. And I call myself that because I do evil with direction and magnitude. Right. So that's Jason Segel, by the way. Well, that's actually Mr. Younger doing a bad representation of Jason Segel, but that's the person that did that. So that is actually a definition of a vector. A vector is a thing that has both magnitude and direction. There's some other rules about it, but the main thing is right now it has magnitude and direction. Technically speaking, I should write V with an arrow over it and then a bar over that. But since I'm in one dimension, that's kind of irrelevant. So I'll say in 2 or 3D, it would be V vector with a bar over it, or V with a bar over it vector, either one of those really. Okay. But what I'm going to do is in a manner just like I did with speed, I am going to say V bar is equal to delta X over delta T. And of course, that is X minus X0 because what we just learned about delta divided by T minus T0. But to be honest with you, we rarely start with T being any time other than 0. So you normally just write that X minus X0 over T. So now let's go back to our earlier example. In front of your house. If the motion took a total of let's say 25.0 seconds, what, and I'm going to call that A, what would be your average speed? Okay, so we're saying that whole motion where I walked to the right 100 meters, turned around, came back 30 meters, and then came to a stop, that took 25 seconds. See if you guys can figure out what the average speed is. And I'm going to assume that we carried that out to one decimal place. So 130 meters is anywhere as small as 129.6 and anywhere as big as 130.4. And the time is measured to 3 sig figs 2, say. So that's 25.0 seconds. And when I do this, I get 5.2. Yeah.
5.2 meters per second. Yeah.
Exactly. So 5.20 meters per second, which we just got by dividing. Now for part B, what is your average velocity. Okay. So that one's going to be V bar is equal to delta X over delta T. We already figured out what delta X was. Hopefully you all remember it's 70.0 meters, and we're going to divide that by 25.0 seconds. 25 goes into 50 twice, and then we of course have 20 left over, which is 4/5. So I'm going to call that 2.8 meters per second. So you see how markedly different that is? All right, so just like I did before, I said there's an average speed, but you should also think about the instantaneous speed, which is what a speedometer would read at any time. But to be honest with you, electronics don't necessarily know calculus. In fact, what they know is basic adding, subtracting, multiplying, and dividing. So what I want you to think about is in the example where I said I was running a mile, when I ran that mile, I told you there'd be times where I'd go fast, like when a dog was chasing me. There'd be times when I'd go slow, when I'm maybe being nosy about what the neighbors are doing. There'd be times when I'd run slow because I'm tired. There'd be times when I'd run fast just because I want to hurry up and get it over with, or I feel jubilant thinking that I can actually get this done or something. But how small of a time interval is that not matter? So for instance, if I did an average instead of over the whole mile, so I take 1 mile divided by the whole amount of time that I ran it, let's say 9 minutes, that's about a decent mile that I ran back the last time I ran. Not a great one, but it's a decent one. So I would take 1 mile and divide it by 9 minutes. Maybe I'd convert that mile to 1.6 kilometers. And then maybe that 9 minutes I'd convert to 630 seconds. And then I could do that, and that would give me the average speed. But what I'm saying is, how small of a time interval do you have to consider taking an average over to be assured that that's essentially your instantaneous speed? For instance, if I took the distance traveled in 3 seconds and then divided by 3 seconds, is that necessarily close enough to my instantaneous velocity? It all depends on how accurately I wish to know that. For instance, if I did that and I did it specifically during a portion of my run where I know I was running pretty constantly, in other words, running exactly the same speed. If I did that and using the proper number of sig figs, I did distance divided by time, distance divided by time, distance divided by time for 3-second intervals. And I really only wanted to know the miles per hour up to 1 decimal place. If each of the miles per hour that I came up with in the 3 cases did not differ in that 1 decimal place, I'd say, yeah, that was close enough for instantaneous. If I had done that same thing sometime where I was in a transition from going slow to going fast or vice versa, then one of them would be a very low velocity, another one would be a middle type velocity, and another one would be a very high velocity, relatively speaking, in which case that 3-second would not be reasonable. But if you actually let the time interval get so small that it's smaller than the amount of time that we make much sense of, in other words, the best hitters have baseball hitters and softball hitters at the competitive level, say college and professional. Those people have some of the best reflexes ever, and they get on the order of a couple tenths of a second, maybe 80 hundredths of a second or something like that. But in that small of a time interval, most people can't register much of a change. If you were dealing with those people, they would. So what do? We take it down one increment smaller. Let's say in the nearest 1,000th of a second, we determine the distance and then divide that distance by velocity. Then we are getting instantaneous velocity. That's just a way we can do it. So it turns out that V instantaneous velocity can be found by saying V instantaneous is equal to, remember the average is delta X over delta T, but I'm going to take that average and do a limiting process where delta T is going to approach 0. And how close you get to 0 only matters when you go to try to compute it. So you want, for instance, delta T to be so small that it's quite a bit smaller than your reaction time, so you wouldn't even notice if it was too big, right? That would be fine. But mathematically, what that means is the velocity is equal to dx over dt. And that's exactly right. Okay, so we've come up with a couple of formulas. We've got the average velocity, we got the average speed, and now we have the instantaneous velocity. And that's pretty good. That's quite a bit of information that we can make sense of. What I'd like to do is motivate that last result another way. I am going to draw another coordinate system. This one's going to be quite a bit different, though. So this one is going to be time in seconds, and this axis is going to be x in meters. And let's say this is 1 second, 2, 3, 4, 5, 6, and that last one should be 7. I'm going to say that this is 1 meter, 2 meters, 3 meters. Now, keep in mind, I actually chose to make the vertical axis and the horizontal axis both have 1 unit be 2 squares wide. We don't have to do that. We can do whatever we want. But when you do that differently, where the distances are separate for 1, then you actually have to choose points off of lines to calculate slope and stuff like that. So just keep that in mind. But let's say, for instance, that after 1 second, we had gone a distance of 0.5 meter. After 2 seconds, we'd gone a distance of 1 meter. After 4 seconds, we'd gone a distance of 2 meters. And after 6 seconds, we'd gone a distance of 3 meters. Okay. So the line of best fit for that goes straight like that. Okay. Now, if you examined a little closer and saw that, in fact, at 1.5 seconds, you were at 3/4 of a meter, then you could say, oh, wow, this looks like a pretty faithful representation of the data. In fact, if you went and saw that 3 seconds corresponded to 2.5, or excuse me, 1.5, and that 5 seconds corresponded to 2.5, and that 6.5 seconds corresponded to 3 1/4, something like that, then all those dots lying right along the line says that it's a faithful representation of the data. Okay. Now, what I want you to do is consider calculating the slope. So M is equal to the slope, which we call rise over run. So if you look at that point, that seems to me to be the max of the rise. The endpoint is 3.25 meters, and the initial is 2.5. And then the run is, in fact, 1.5 seconds. You could technically say 6.5 minus 5.0, but I'm just going to call that 1.50 seconds. So the slope is equal to what number? I'm going to do 3.25 minus 2.5. That gives me 0.75, and I'm going to divide that by 1.50, and that gives me 0.50. Now, when I subtracted the 3.25 minus the 0.25. That gave me 0.75 to 2 sig figs, and then I divided it by 3, so I only get 2 sig figs now. So I have to actually write it like that. So that's the slope. The slope is 1/2. Can anybody tell me what the units of the slope are? Something you don't normally think about in algebra because you always just use axes that are just numbers. But in physics, you know, we're doing axes that have units. So anybody want to tell me what the unit of
Meters
that
per
point?
second.
Yes,
M
because we
over
did
2.
meters in the top and we did seconds in the bottom. Now, what I want you to realize is that has the right size and the right units. Do y'all see that that looks like a velocity? In fact, that is what we just discovered on a x versus t graph. The slope equals the velocity. I'll also say on a x versus t graph, the height equals the position. What I mean by that, well, if you go right here, that height appears to be 1.75 meters, which corresponds to how far you were away from the origin at that point in time. That make sense? Now, this straight line has a constant slope. And that's the hallmark of constant velocity. In fact, Galileo was the first person to really force us, as far as we know, force us to consider distance and time simultaneously. In fact, he had just been put in-house arrest from suggesting that the Earth was actually orbiting the sun and refusing to recant until finally they showed him the instruments that they would use to cut his entrails out of his scrotum and show it to him. And he, at the ripe old age of 70 something, decided, okay, maybe I'll listen. Okay, so he said, yeah, it doesn't move. And then they said, okay, well, luckily he was a friend of the Pope, who used to be his friend even before he became the Pope. So he got in-house arrest, unlike Giordano Bruno or Joan of Arc, who actually got burned at the stake. So he was able to go home, but he was no longer allowed to study astronomy, what we call astronomy, what they would have called astrology. He couldn't study that anymore. But he had already figured out some stuff about astronomy. And what we knew, and everybody knew, is that Jupiter had these specific little satellites that moved. And for some reason, they never got left behind by Jupiter. So he felt like he needed to understand motion. So he started by considering dropping objects, but then he realized, wow, those things fall really fast. I can't make heads or tails. I can't tell if they're speeding up, they're going at a constant speed, they're slowing down, or anything. But what he did figure out is that trigonometrically, there's a ratio between the acceleration down an incline and vertical acceleration that's related to the steepness of the incline. Therefore, he was able to study inclines and let objects roll down it. What he found was that when an object rolls down, it speeds up. When an object rolls up, it slows down. And he argued that when it rolls at a level surface, it should not change its velocity at all. And in fact, what he did was he defined velocity to be a constant if it always covered the same distance in a given unit of time. So Galileo if in a given time, actually, whoa. If in a given amount of time, for example, 1.0 seconds, the object always traverses the same displacement. Here's a case where you could use displacement r distance, because I'm really talking about mostly things going in straight lines, but technically you have to use displacement because I defined velocity to be the change in displacement divided by time. So in this case, if in a given amount of time, the object always traverses the same displacement, then the object has a constant velocity. Okay. Now, technically, since that's velocity and it's vector quantity, it not only has to cover the same distance in a given amount of time, it also has to not change direction at all. So that's the only difference in going from 1D to 2D or 3D. So that's what the definition of constant velocity is. And in fact, if you look right here and you take this little bit of time, you'll get a slope. That's a velocity. You do another bit of time and another bit of time. All of those point to you getting the same amount of time. So in this case, you might say above in each 1.0 second interval, 0.50 meters is covered. So the velocity is constant. Okay. But that also means in each 0.50 seconds, 0.25 meters is covered. So that's another way of saying it. Check. R in each 2.0 seconds, 1.0 meters is covered. So that's another one too. So each of those, all three of those are exactly the same thing. If I cut the interval of time down by 1/2, then I expect I cut the distance down by 1/2. If I double the time, I double the distance, so on and so forth. All of those are definitions of constant velocity. So that makes sense to everyone? All right, now if I could do the same thing, let's do this. I'm going to steal this graph, and I'm actually going to steal I think I'm going to end up stealing the link above, because that's just what happens. Yep, notice it put the link in there too. That wasn't quite what I wanted. Let's do it over here. Okay, so I can do that, and I'll just stick it right on top here and pretend like nothing's happening, and it'll all be just fine. Okay. So now that I have that, that's another thing. Now, what if instead of me having those particular data points, like I said, what if I had a 1/4 of a meter in 1 second, and then I had a 1/2 meter in 2 seconds, and then in 4 seconds, I had 2 meters, and so on and so forth. Then the motion looks like that. Slope is changing, which means V is not a constant. Actually, let's write that somewhere else because I tried to fit it in there and I just shouldn't have tried that. So slope is changing, which implies V is not a constant. So we might actually wish to calculate the velocity by considering the average velocity between that point and that point, or maybe we might even start between that point and that point. And you can see clearly, since we figured out that the slope is the velocity right here, the tangent line for this new graph is, in fact, I'm going to write this in, let's say, purple. So this is the tangent line at that particular point. At this particular point, this is the tangent line. At this particular point, this is the tangent line. Okay. So if I took those averages, because it's so obvious that the slopes at the beginning and end of each of those intervals are different, obviously they would not be good candidates for the instantaneous velocity. So if I zoom in on that graph real quick, what we can see is this to this, this to this. That's called a secant line. You don't need to know that for my class, but that's just something mathematicians use. This is another secant line, but you can see here the slope is pretty close for the tangent line to the slope of that. Here, not so much, right? But if you keep going and choosing smaller and smaller time intervals, then you will get an instantaneous velocity. So in fact, V instantaneous is equal to the limit as delta t approaches 0 of delta x over delta t. So in other words, that delta x over delta t, that's just our slope. So you're calculating the average, but if you let the time interval, which this would be t1, this would be t2, which equals t1 plus delta t. As you're letting that delta t get smaller and smaller, eventually your secant line will become almost parallel to the tangent line or close enough to parallel, and you'll get the actual instantaneous velocity. Does that make sense? All right. So now we can make yet another graph. This time we can make the graph, instead of making it position versus time, we can make it velocity versus time. So this is velocity in meters per second, and this is time in seconds. And I'm going to say this is 1, 2, 3, 4, 5, 6, 7, and that guy over there is 8, and this is 1, 2, 3, 4, 5. So this is 5, this is 1, this is 1, and this is 7, like that. Okay, in this case, you could have a string of dots that look like this. And then your line of best fit would be like that. You could also have a string of dots that look like this. Let's say I'm going to choose a different color this time. I'm going to say this time it's this one, this one, this one, this one, in which case the line is like that. Or you can even have, for instance, this one, this one, this one, and this one. And there, I'm actually going to use a different line color this time. You'd have that. Now, again, if you calculate the slope, or you calculate the slope here, that's actually equal to 2.5, excuse me, that's not 2.5. Yes, that's 2.5 meters minus 2.0 meters divided by, now my run is 2.5 seconds minus the other one, which is just 2.0 seconds. So I get 1.0 meter. Oh, excuse me. That's meters per second, meters per second. Sorry about that. That's a very important thing here. Let me make sure you guys can see this. I wrote it just haphazardly, not paying attention. That's bad. That's supposed to be 2.5 meters per second minus 2.0 meters per second. And that gives me 1.0 meters per second per second. I think you can see from that, that is a change in velocity per time. In fact, it's the rate of change of velocity with respect to time, and that is called the acceleration. So that stuff we just found out for a position versus time graph, we just found out something similar. This is average acceleration. And we call that A with a bar over it. And what we see is A with a bar over it is delta V over delta T, which equals V minus V0 over T minus T0. Again, we hardly ever use T not being equal to 0, but twice I have today. And then from that, you probably see that A instantaneous is in fact equal to the limit as delta T approaches 0 of delta V over delta T, which is dV dt. And that's exactly what we were shooting for. So we now have two things that can help us with regards to acceleration. Now, normally we say like a car can go from 0 to 60 in 4.00 seconds. Okay, that's like a typical right off the line Mustang or Camaro or something like that. Some of the newer ones are even faster than that. The Tesla Plaid can do a flat 1.0 seconds. That's pretty impressive. But with that in mind, that means the average acceleration would be 60 that'd be 60.0 miles per hour minus 0.0 miles per hour divided by 4.00 seconds. That's going to give me 60 over 4, and that is in miles per hour per second, which gives me 15.0 miles per hour per second. That is really the best measure that a car dealership can give you if you want to know the car's acceleration, okay? Because it's a direct measurement of it. Now that we have this kind of stuff, we can do things like A is defined to be dV dt. If A equals a constant, then I can do this. And this process, pay attention, this process you're going to have to do too. The book or the homework sets or the practice tests will give you A as a function of T or A as a constant, and then ask you to make up these equations. So what I'm going to do is I'm going to say A is equal to dV dt, and I'm going to take that, remember this is a constant, I'm going to take that and multiply both sides by dt. So I get a dt is equal to dv dt times dt. And now I'm going to integrate it like that. And of course, this is an indefinite integral. So I'm going to get at plus c1 is equal to v plus c2. This v is really the same thing as v final, but it's also v as a function of t, because when I solve for v, I'm going to have a function of t on the other side. So now I've got v is equal to c1 minus c2, oops, plus at, which I'm just going to redefine this constant and say that v is equal to c plus at, and then I'll say if the object had an initial velocity, let's say an initial, oops, I don't know why I crossed my L there, but that's not good. Velocity of v0 at t equals 0, then you can make this conclusion. You'd say v0 is equal to c plus a times 0 implies c is equal to v0, and we'd have a very useful equation, v is equal to v0 plus at. That's one of our kinematic equations. Now we can use, since v is equal to dx dt, we can do the following. I can say v0 plus at is equal to dx dt. I can multiply both sides by dt. And then I can integrate both sides, and I'm going to say the integral of v0 plus at dt is equal to the integral dx dt. And by the way, all I'm using on this right-hand side is the fundamental theorem of calculus. The integral of a derivative is basically the original function. That's why I got v before, and this time I'll get x. So in this case, what I'm going to get is v0t plus 1/2 at squared plus c3 is equal to x plus c4, which I can solve for x, and then I'll get x is equal to 1/2 at squared plus v0t plus c3 minus c4. If x equals x0 at t equals 0, then we have x0 is equal to 1/2 a times 0 squared plus v0 times 0 plus, let's call this a new constant, just plain c. Then c is equal to x0, and we have another fundamental kinematic equation. X is equal to 1/2 at squared plus v0t plus x0. And we've now exceeded the time. I will tell you there's another equation. I'll derive it next time, but the other equation I'm talking about is v squared equals v0 squared plus 2a times x minus x0. And that's what the problems for this chapter is about, is applying these equations, which are only true for a equals constant. A equals a constant. And a equals a constant. That has to be true for those equations to work. If they gave you a function like 3t squared plus 27t minus 4, then you'd have to go through that same integration process and then use their initial conditions, not the generic ones I used, or you could use the generic ones I used, and you could get different kinematic equations. But that's basically it. We're essentially through section 2.5, 2-5, and you can definitely get started on your homework. When we meet next time, actually, I set the homework due to this coming Sunday, and that's not right. So I will definitely be setting that back because we're off by a day where we didn't have class on Monday. So I will probably push it back just to the following Sunday to get us in the groove of going, having everything due on Sunday. But I'm definitely going to move that back, and we'll have a meeting on Monday, both for your lab as well as for your lecture. By the way, I might also open up the lab section in Canvas just because I have some students attending our lab that aren't from our class, and the easiest way to deal with all students at once is to put them all in one class for the lab. So I might do that. If you see another one pop up, it'll have the lab L01B as the section, and you'll know that's what that's for. Okay. I'll also send you an email to let you know. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions, but thank you for coming, everybody. Feel free to ask me any questions.
Good night.
Good night. Have a good one.
Thank you.
Good night.
See
Thank
you
you.
next time.
You're welcome. Thank
Thank you.
you.
I had a question about when doing like, or taking, for example, when we had curves or free falling objects. So if we look at the objects in terms as the slope of the tangent, could we also assume that that is also the velocity? So if the slope of the tangent is decreasing, that would mean the velocity is decreasing, but that doesn't determine whether acceleration is decreasing or not. That's
Exactly.
what my question was.
Yeah, so you
Okay.
actually have to go another level, and you also got to be very careful about whether you're talking about a position versus time graph versus a velocity versus time graph.
Okay.
So
Okay.
yeah, on a position versus time graph, the slope is the velocity, and therefore an increasing slope gives you an increasing velocity. In order for you to calculate that average acceleration, you could take the final velocity, the final slope minus the initial slope, and divide it by the time interval between them, and that would give you the acceleration. But you couldn't just read it off the graph like a slope. You'd actually have to do some calculations.
Okay.
If, on the other hand, you did a velocity versus time graph, then you could just take the slope, and that would be the acceleration.
Okay.
Does that
Okay,
help?
that makes sense. Yes, it does.
Kim, did
Yeah, I
you
just
have any
got,
questions as well?
yeah, I just have a question about like a bonus problem.
Yes.
How much is that worth for like all the bonuses? Is that like per chapter or is it like let's say it worth like 2% of the entire class grade?
Oh,
Or
are you asking about how much the extra credit is worth?
yeah, like
Okay. Yeah,
the
all I
yeah.
do, I'll actually, speaking of which, I forgot to tell you, yeah, I made your syllabuses over the break and posted them. But anyways, yeah, what it says in there is that when you do these extra credits that I assign, basically what I do is I up the number of homework grades that I drop, because I drop the 2 lowest grades right now just from the syllabus. So if I offer 1 extra credit homework, I'll make that 3. And if you actually did it, then and I said you did it well, then you get 100 there, and that 100 will replace a lower homework grade. If you didn't do it, you'll get a 0 there, but I increased the number of drop grades by 1, so it wouldn't harm you. That's the way that works.
Right. So say I have like a 60 or 70 on the chapter 1 homework, right?
Mm-hmm.
Like 100 on the extra credit. Does that mean like the extra credit replace the homework and I get 100
Exactly. Yeah,
for the
that's what
homework?
that's exactly what it does. So if that 60 was your lowest
So
homework grade, and you'd already dropped 2 that were automatically dropped, then yeah, that 60 would become 100 because of that extra homework or extra credit.
yeah, but is it like does that 100 have to be from like every extra credit combined or just
Yeah,
like that one chapter?
each one takes the place of 1 homework assignment.
so okay, so the last one you got like 2 extra credit. I
Mhm.
only did one of them. So does that mean I will get 50? 50,
Yeah.
50?
So this past week we had 2 homework assignments. One was conceptual. That's not what I'm talking about. The other one was a homework problem. So if that homework set turned out to be bad, you could in principle get 100 on the extra credit, and that would replace that bad grade for that particular one.
No, like I mean, like we got like 2 extra credit homework, right?
Right.
Because that's what we got last time, right? So is that I only got 100 on one of them. I didn't do the other one. So
Yeah.
do
So
I am I still getting 100 or no?
yeah, so what I do is I give you a 0 or 100. So if you do a homework set, like a chapter 16 homework, which is extra credit, that's kind of a lot. If you score, I'd probably say somewhere along the 80 to 85 range. If you scored that in it, I'd go ahead and give you 100 for that. It just count as a 100 grade.
Oh, so currently I have like a 54.33 over 70 on chapter one homework. But the
Gotcha.
extra credit number two, I got 100 on it. I didn't do the extra credit number one. So do I get
So that
100?
means you now have a 100 homework average.
Oh, okay.
Yep.
Okay. All right. So it don't matter what if I just do only one of these extra credit or both of these, I'll still
Right.
get the grade from which of these.
Exactly. But if you make another homework set and you get a bad grade on that, then doing that second homework set would have erased that one too.
Got you. Got you.
That makes sense.
Yep, that makes sense. All right.
All right.
Thank
Well,
you.
have a good one, Kim. Anything else I can help you with?
No, that'll be it. All right. Have
right.
a good night, sir.
You too. Have a good weekend. Bye bye.